Good afternoon. My name's Kieran, and I kind of feel lonely up here. I've never spoken to a room this big before, so I feel like Caspar said I need to do a dance. Okay, so I'm from Australia. I work part-time for a business called Frontier Labs. We've got a booth outside, but I have a business and I work as a consulting ecologist, and which I've been doing for 30 years. The PowerPoint presentation that I'm going to present was developed by Michael Maggs, who's one of the engineers at Frontier Labs, and then the software that I'll demonstrate was also developed by Michael. The data I'm using that I'll demonstrate with is data I've collected on one of my projects on a threatened bird that I've been monitoring for a bit over 9 years now. And the localisation package that Michael has developed has allowed me to work out detection distance, acoustic detection distance, and it's actually shown me that I've been making a few assumptions, incorrect assumptions. But anyway, the software package itself, Michael's called Studio. It hasn't been commercially released, but he's happy to share it with people. But there's a caveat. You really need to use Frontier Labs hardware to generate the data that is compatible with the software package. And there's a few logical reasons for that. Okay, so has anybody here attempted to localise sound in space? Have you ever tried, who's tried acoustic localisation? Yep, a couple. Okay, for the rest of you then, close your eyes. I'm serious, close your eyes. Actually, this isn't going to work, I've just realised something. Okay, keep your eyes closed. So see if you can point to where I am. Yeah. Okay, so I'll ask the question again. Who's tried to localise sound in space? Yeah, we're doing it all the time. And we do it with a microphone array, 2 ears. But passive acoustic monitoring's allowing us to answer questions that were very difficult in the past, especially with cryptic species. One of the problems with passive acoustic monitoring is it's very hard to work out what your sampling strength is, your spatial sampling strength. And that's because we're dealing with complex biodiversity and complex landscapes, and different things are doing different things at different times. And we tend to make a lot of assumptions. So Michael has developed a tool that works with passive acoustic data, and we've now tried it on, well, I use it with the bird I work on, koalas, this bird here, which is a bittern, which lives in reed beds. Very difficult to actually to find and see, very cryptic, but it makes a booming call that propagates quite well over distance. And if you're dealing with a species that produces a distinctive signal that you can identify as an individual signal, you've got the possibility to localise it. Now, what we're going to explore now is never going to work for things like frogs that call in a chorus, because you can't identify individual sounds in passive acoustic data, because you don't have enough distinct features to the individual sounds to identify them as individual sounds. So the software package, literally, the way I think of it is it throws the sound onto a map, and then it looks for points of correlation. And it doesn't always do that. It doesn't always find the correct points of correlation, because we're dealing, in the case of a lot of projects, we're dealing with noisy landscapes with a lot of complexity in the sound. What you need, though, is to make sure that you can find the same signal on at least 3 recorders. So then it doesn't, as you'll see when we look at the sample data, it doesn't matter what's going on in the surrounds of each recorder. What does matter is that each recorder has got the signal you're looking for. So you can make sense and you can localise quite noisy data. And it helps if the noise on the different recorders at the different locations is different. So if you've got a small frog or something like that calling at one recorder, making a lot of noise, and it's not the sound's not travelling far enough to be picked up by the other recorders in the array, that's great, as long as the signal you're looking for, your bird call, is on all 3 or 4 recorders. Okay, so this slide is based on a data set that was sent down to us from North Queensland, and you can see the little icon for the koala. That was what we were really interested in. Also within the data was a call by a bat called Ostronomus, which sits, it's calls at about 13 to 15 kilohertz, and it was in the data too, so we localised the call of that, and obviously it was moving. Now, the interesting thing is that koala, his name was Athie, A-T-H-I-E, because Athie was found at Atherton on the Atherton Tablelands, and was the first koala, the actual specimen of a koala that had turned up for decades that far north. Anyway, Athie wore a collar for 3 months, and in that 3-month period, the tree kangaroo and mammal group in North Queensland knew where Athie was all the time, and Athie covered 13 kilometres in the 3 months that he wore that collar. So at a time in Athie's movements, he moved around within an acoustic monitoring array, and some of the acoustic recorders ran the localisation firmware that you need to use to collect localisable data. And has anybody seen the booth that I've got out there? Anyway, there's a range of hardware models that you can run this localisation firmware on, and what it does is at the commencement of each audio file, it boots the GPS receiver up, gets a time clock fix with the GPS satellite network, and at the end of each audio file, it boots the GPS receiver up again, and it gets an end time for the audio file. So it bookends each audio file with a satellite network synchronised time fix. And on board, the recorder's got a crystal clock, which you get time drift. So ideally, when you're collecting localisable data, you don't want your files to be any longer than about an hour. I usually collect the files in half-hour chunks. And you've got to be in a landscape that allows for some GPS receptivity. So, this was originally this was designed to be done as a workshop in a small group with a room where we could pass USB sticks around and share data, which we can't do here. But I'll just talk a little bit about recorder setup and array positioning. So, there's a few people here who tried to localise, but who else has done work with passive acoustic data sets? Yeah, a few of you. Okay, so you're sort of familiar with acoustic footprint, from the animal generating the sound, an acoustic envelope, i.e. the distance at which a recorder can find your sound. Are familiar with those terms? Yep. Okay, so what you've got to do is make sure in your localisation array that your array spacing allows for a signal from an animal to be captured by the recorders in your array. Now, if you're not sure where your animal is going to be, you can put more recorders out to cover the total area to make sure, but it's the spacing that matters. So for koalas, we can find koala signals in acoustic data sets at about 7 to 800 metres. So that the data set that the tree kangaroo and mammal group was collected with, that array was, the recorders were at 400 metre centres. And it doesn't matter so much, the recorders themselves don't have to be accurately positioned relative to each other, but you have to know accurately where each recorder is for this to work. So, you know, if you've got a large array with large array spacing because you've got noisy, loud animal, loud signals, you can push your array right out, and then you don't have your error in measurement of position is not so critical. Okay, there's a few other limitations or caveats on the way you've got to collect the data to be compatible with the analysis software. So the recorders have got to be collecting the data at 44.1 kilohertz as the sampling rate. Single channel recording. Some of the Frontier Labs recorders will record in stereo, so you've got to tell them to record in mono. And if you want to, you know, sample a long time period, break it up into chunks. Don't run. Tell the recorder to collect 3-hour files or 6-hour files. Probably, you know, half hour to an hour maximum. But it's critical that the recorders are sampling at 44.1 kilohertz. And at the moment, ideally in a fairly flat plane. Michael's working on a 3D analysis package, but that's close to ready for release for people to test, but a few more months. But for the bird I work on, the eastern ground parrot, it lives in a dead flat landscape, and it is in the heath on the same plane as the recorders. You need at least 3 recorders, but you can use more, as many as you like. Now, Michael thinks that you can only localise sound within the array, but with the work I've done on ground parrots, it's giving me really good position fixes outside of the array. All you really need to do is to make sure that the array you can really accurately position the recorders. But yeah, with repetition, I've got fairly good confidence that the positions of birds outside of the array are accurate. So, like I said earlier, that the geometry doesn't matter that much. You just need to make sure that you can find signals on at least 3 recorders, and ideally roughly triangular, but it's not critical. Now, has anybody done array work with passive acoustic recorders? Yeah. How big have your arrays been? Yeah, okay. And how many recorders? Whoa, okay. Okay. Yeah, so when you're doing array work, if you're trying to sample space, it can be sometimes, especially when you're dealing with landscapes that are complex, it can be hard to work out where to put recorders and to work out how to space recorders in an array. If I do a lot of work in these heaths, and I usually run the arrays as offset grids. That gives, well, certainly in that work, it gives me the best coverage. Does anybody use Trimbles or any of the devices to give you an accurate position on ground? Yeah, so we use them too. The recorders themselves have got onboard GPS, and for the LT model, it's about as good as the recorder itself will give your position about as accurate as a handheld Garmin, which is fine for arrays at 400 metre spacings. Okay, so this is all fairly obvious stuff. Deploy your recorders, make sure they get a GPS fix, and they can find a GPS fix fairly easily, which means if you're in forest, you might have to look up and move around a bit to make sure that you've got, you're not surrounded by too many trees. Now, you can use sound to accurately fix the position of your recorders, but for the work I do, it's no good because the array spacing is too large for a sound to propagate around the entire array. So you need, if you're going to use sound like a loud clap or a shout, you do it from the position of several recorders. You need to be able to hear that at the other recorders. Okay, I mean, you'll watch me do this in a minute, but what the software does, or sorry, what the hardware does, is it puts an accurate timestamp effectively at the start and the end of each recording. So the file names themselves are really long, cumbersome file names, so it's not a good idea to use the recorders to collect localizable data if you're never going to use it as localizable data. So our recorders, we don't run them with the localization firmware all the time. So the other thing that's important is that when the recorders are running, they create a log file that they put in each daily folder. When you're analysing or choosing data to analyse for localisation, you've got to make sure that that log file stays within that folder for that day. And the log files are just called log, so if you mix them up between folders, you've got a problem. Okay, so collect your data. What I do is I set a folder structure up for each recorder. I just number them. I copy the data from each recorder into each folder, and then I go and have a look at it. I generally use Raven. I have a look at it because I find Raven quite easy to use for looking at spectrograms. I make sure I've got the signals that I want, and then I'll analyse them with Studio. I will look at this in a moment. Okay, so you've got essentially three analysis methods within the software package. You've got time distance of arrival. You've got two cross-correlation analysis methods, and I sort of switch between them when I'm analysing individual sounds, just to make sure that, as you'll see, that the position fix that Studio gives me, it's using the lines of correlation that I'm wanting. And when you're dealing with noisy data, it doesn't always do that. Okay, and on the right, that's a cross-correlation analysis, and as you can see, that's noisy data, and it struggled to try and work out which sound you were trying to localise. Okay, shall we have a go here? The cables. Oh yeah, we're good to go. Okay, so just quickly, the data we're looking at is some audio recordings of this bird. It's a threatened bird called eastern ground parrot. You've probably heard of a bird called the night parrot. Have you heard of night parrots? Thought extinct. This is a congener to the night parrot. also threatened and in decline. And as you can see, it's a green needle that lives in a green haystack. We've tried lots of different techniques for detecting and monitoring this bird, and passive acoustic methods are yielding the best results by a long shot, much better than human collected data. Okay, so what I've done is I've just saved a series of files into some folders, and you've just got to remember that I'm an ecologist, not a tech guy, and that I'm not going to be as slick at this as Casper will be. Right, so what Studio's done is it's pulled, as you can see, it's pulled, as I move around, it's pulled the location of each recorder out of that location log file, and it's put it on a map for me. Now, this was the array was a 5-recorder array originally when I laid it out, but due to my error, I didn't schedule one of the machines properly. We're missing a recorder. So, as you can see, this recorder, these are on 100-metre spacings. I'm not likely to find a signal on this one common to these. So what we're going to do is we're going to ditch the data from recorder 24952. Now, what I can now do is, because I'm confident that those locations are accurate, because I was using a Trimble, what I can do is lock all of those positions, and then I can look at the audio. So now, I mentioned before, this is quite a noisy site, and I'll show you what I mean by noise. That's a 737 taxiing adjacent to the study area. These birds, this population that I'm monitoring is actually adjacent to an airport. So you're dealing with a lot of confound. Hold on, what have I done? Okay, let's go. That is an eastern ground parrot call. And as you can see, it's made up of a series of notes. Doot, 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 doot. And each note is, as you can see, distinct from the others. And when they call, they almost always do a slightly different arrangement in the notes. So a single eastern ground parrot call can be identified quite easily. So can you see the complexity in that? You know, you can literally count the number of notes, and if there's another one calling at the same time within this time window, you can easily tell that that other call is a different sound, and that's what makes this bird so easy to localise. So when it calls, it's down in the heath, in thick complex heath. You can't see it, and it's usually stationary. There is a call that they make in flight, but it's different to this call. So I know this is one of the calls it does in its dusk chorus when it's stationary in the heath. So what we can do is, because I wasn't physically there, I wasn't able to validate or verify the location of this bird, but what I've been doing is using replication to obtain some degree of confidence. Okay, put a box around each call. So let's start with, just make sure that it's matching the audio properly. Yep. Then we go to map view. Right. So that's using the TDoA option for localising the sound. So what we can do if we like is, let's put a red pin Do you want to see how close those positions are on the ground? But they're different sounds that we're localising. They're not the same sound. Okay, let's go to the fourth one. Shall we do another one? Maybe one more. 1, 2, 3, 4, 5. Let me see it. Now we'll go to number 6. So that's what, 1, 2, 3, 4, 5 replicates, 5 different sounds that have been localised on a map by a bird that's stationary when it's calling, within an array of 100 by 100 metre spacing. So what we can now do is we can, if we want to, we can export those positions as a CSV file, just as click button. Now what I wanted to share with you was just for a moment, have a look at these recorder positions. So the bird is between 25009 and 41157, okay? So if we look at the audio, what do we say? It's between 25009 and what was the other one again? Sorry, go back. 2509 and 41157. So it was between that recorder and that recorder. So can you see the signal strength on the spectrogram? Can you see that it differs? The signal strength is quite different. These were the same machines, same microphone, same gain setting. Why would that be? Yet the furthest recorder from it, which is this one, 45041, the signal strength is actually slightly stronger than it is on a closer recorder. So for years I've been monitoring these birds with passive acoustic data sets, and I've been assuming that signal strength on a position within an array indicates position to proximity to a recorder. If the signal strength is strong, close to a recorder, I've been assuming that that bird is close to that recorder. Where could I be going wrong? Yeah, such a simple damn thing. All these 9 years I've been assuming the bird's facing towards one recorder and away from the other two. And it took this for me to realise. But anyway, can you see the utility of the tool? And for somebody like me who's a field ecologist, having literally a press button analysis option that allows me to localise sound in space is a pretty powerful tool. So it's the simplicity of using this that means that somebody like me is actually using it. I think it has value. So, look, if Michael's quite happy to share this software with people, but there's the problem you'll have to use the recorders that generate the data that you can localise with it. So feel free to come and talk to me afterwards, and I'll put you in touch with him. But that was, 26 minutes, a bit quicker than I thought. Yeah, but any questions? And please, an ecologist, so yeah, Pastor. Yes, okay, so, yeah. Has anybody here tried to localise sound using TDoA on spectrograms? Has anybody tried to do it? So a few years ago, before this was available, I ran some stereo recorders out at this site, because I was trying to work out what my detection distance was on audio recordings. So what I did was I laid recorders out, 2 mics on extension cables, got them, I think it was 20 metres apart. I'm not a mathematician, but I crunched some numbers and I figured at a 20 metre spacing, I would be able to obtain a line of direction to a sound. So I then went, collected some audio, measured the time of arrival, like I've just, on calls like this, repeatedly measured time of arrival, measured time of arrival, did the maths, obtained a line of direction, and I thought, yep, you beauty. Then I stepped back from it a bit and thought, where could I be introducing error in this process, remembering that I'm not a mathematician. So I thought, okay, maybe I haven't thought about variability in measuring time of arrival of these calls, and they're it's biological sound. There's a certain fuzziness to it. So if you try and measure these calls, the time of arrival of one of these signals on a spectrogram, what do you choose in that signal to measure for your time of arrival? And it doesn't matter what you choose, the start or the end of each note. If you repeatedly try and measure it, manually on a spectrogram, my error anyway, in the measurement was so great that it was giving me the maths looked like this on the ground. So it was useless. I'm sure, this was 5-6 years ago, I'm sure somebody could do that now, with a much greater degree of accuracy. But that's why when I did that, we've lost it. Okay. When I did that TDoA arrival analysis, it was a fuzzy patch. Oh, we've got it back. Sweet. Thank you. So if we try that again, we'll just pick one because we've got time. Let's pick that signal there. Hold on, where are we? Hold on, I've got to go back to localisation. Okay, so audio view, okay, right. Are they matching well? Yep. Okay. That's why you've got that fuzziness in a TDoA analysis. But you can use it to confirm, because in the spectrogram, if you have a look, the box I've put around each signal is around signal and noise. And what you tend to do when you're looking at spectrograms, when you're looking for particular signals, you forget that there's other stuff going on in that sound. And what you're doing with Studio is all of that sound is getting basically thrown onto the map. So when you're dealing with noisy data, TDoA can help you confirm that the point of correlation that Studio thinks you're trying to, the sounds that Studio thinks that you're trying to locate, this can be a way to help you confirm that. Yeah, any other questions? Well, this version's available if you want to play with it. Yep. Yeah, you're welcome. If you want to try it. Yeah. The version that's still in testing is a 3D attempt to use the same mathematics. Yep. Yeah. Anybody else? Yeah. Okay. Thank you.